Um, like let's so today we're going to uh actually the first two questions are going to be prompts from the USML, and then I'm going to talk about a topic that is very important for the aim. It's 3D. It's like this idea of 3D geometry. Um, like and I'm gonna present like two questions on it because like the aim is coming up in 2 weeks. And I want to talk about this idea of 3D geometry, that you you need to like because I you need to be able to use in solving problem because I look at the recent aiming problem, like there are actually two prompts on the aim. Like the students requested to me to cover them, and I noticed that there are two questions on the recent aim that is like in 3D geometry. um like I just wonder like last year you said that you solved like I know that you solved 12 questions on the aim. Which one did you solve last year? Like do you remember do you remember this question? Like it was on last year's aim.
I don't remember. Oh,
Okay.
yeah.
Okay. I guess like you did. Like, okay. Yeah. Because like today we're gonna talk about like the second half. Like I want to spend some time talk about 3D geometry. But like before that, like I want to finish off like these two questions first. Okay. Yeah. Um. So basically, like I talked about in this diagram, like last week, we had like 10 minutes to talk about it. Like there are a lot of cyclic quadrilaterals. Hey. And here there are two things we need to prove. Okay, is that like just here we have a triangle ABC, and we have the inscribed circle, and then we have the tangent points, and then we have the midpoints of the triangle, and then well, so that's where we get E and F, right? And then we're going to draw some lines. We're gonna draw the line EF. Yeah, we're gonna draw the line EF, and then like basically it connects the tangent points, and then we draw the mid segments. We draw mid segments PN and MN. Okay? Mid segments intersect at U and V, and then we want to show that point V. So the first thing is we want to show proof that V is on the ray CI. Okay. The way to prove this is it was like if you draw in circles, you should see that there are a lot of cyclic quadrilaterals. So the here is actually like if there are problems like with very few cyclic quadrilaterals, is usually a lot easier. Here there are a lot of cyclic quadrilaterals. It's like which one do we really want to use? Well, probably the one that goes through V. Like probably like one that goes through V. Right? Um, like So the one that we actually use is actually this one here. Okay, I'm gonna draw in red. You see how I start M. Hey, this is the one that we're gonna draw. Okay. Uh, so we have proof that B, like we want to prove that BVUC is a cyclic quadrilateral. Okay. Well, why is that the case? Right? Well, the reason we know that this is a cyclic quadrilateral is actually not by angle tracing, but rather we want to show that M is the center of the cyclic quadrilateral as well. Okay. Basically, let's try to find out like what's the length of MB. Okay. Like it's pretty easy to see that because like we construct M is the midpoint of the side AC. Okay. So therefore we can let the length of BM is equal MC is equal to the length A over 2. Okay. Because like the side opposite from angle A can be written as little a. Okay? So therefore, we have the BM and MC are both A over 2. Okay? And then notice that we are drawing tangent points. We have tangent lines here. So let's do some length chasing. Let's try to find what is the length of MV. What's the length of MV? Okay. Well, MV is equal to MP minus PV. What's MP? MP is simply the length of AC divided by 2. So that's little b over 2. And what's PV? PV is equal to AF minus AP. Because we know that this is an ice. This has to be an this has to be an this is going to be an oh wait, hold on. Do we know that that's an isosceles triangle? Okay. Well, we want to show that this is an isosceles triangle because here we don't know if that is not. Well, at the end we want to show that this is an isosceles triangle. Well, we know that this angle here, this angle is well, because of parallel line. Oh yeah, yes, sure. It is the isosceles triangle. Why is that an isosceles triangle? It's because you know that angle PVF is, well, we know that MP is the mid segment. Is that because MP is parallel to AC because of mid segment? Then we know angle PVF is equal to angle AEF. But the thing is, like, you know that by the two tangent theorem, two tangents, we have the angle, well, we have the AE is equal to AF, so therefore we have the angle AEF is equal to angle AFE. So therefore, we have an isosceles triangle. Like essentially, we have a lot of isosceles triangles here. So we can write that. Yeah. So basically, the AF is, PV is essentially PF, which is AF minus AP. Well, AP is half the length of AB, so that is C over 2. And let's try to find what's the length of AF. So here we have B over 2 plus C over 2 minus AF. Let's try to find what's the length of AF. Well, to find the length of AF, we're going, like, how do we do it? It's, well, we use the inscribed circle thing, right? Like basically, we have this triangle, like in the arbitrary triangle ABC. F is the tangent point on the side AB. Like we do the two tangent theorem, like X, Y, Y. So we want to find X. Z, Z, and we have the X plus Y plus Z is equal to A plus B plus C over 2. So therefore AF is equal to X. So X is equal to A plus B plus C over 2 minus the length of YZ. No, minus the length of Y plus Z. So what is that equal to? Well, minus the length of Y plus Z, that is minus little a. So this is equal to B plus C minus A over 2. So we get this is equal to, wait, hold on. Oh yeah, that's fine. So you have the B plus B over 2 plus C over 2 minus B plus C minus A over 2. What's nice about this is that the B plus C cancel out. So you just get A over 2. Ah, that's very nice. We have the length of MV. By doing the semi-perimeter stuff, we get that as A over 2, which is the same as the length of BM and MC. And you can pretty much do the same thing, or you can just say that by a variable symmetry, MU has to be also equal to A over 2 by variable symmetry. Because like you look at the diagram, like the triangle is like, you didn't, like angle A is not a special angle within this triangle. So therefore, if you use the point M, like it's true for V, it has to be true for U. But you can do the same thing and prove this. Okay? But on the use mode, you can just say that similarly. We have so like basically you can say that similarly. So basically what we just did is that we prove that MB equal to MC is equal to A over 2, and we have the MV is also A over 2. Okay, so similarly we have mu is equal to A over 2. Okay, so therefore we have the 4-point cyclic. This is one of the first times where we prove like actually not many times, like because like we usually prove like a 4-point cyclic by doing angle chasing. Okay, here we're doing some length chasing to prove that the 4 points are cyclic. Okay, so here we can say that we have the B V U C cyclic. Okay, with the center at point M. Right, because like those 4 points are equidistant from point M. So if you draw a circle, well, the 4 points must be on the circle. Okay, so that is like that's the what we have right here. Okay, and then what do we? Okay, well at the end we want to prove that point V is on the angle bisector of angle C. Right? Well, how do we do that? Well, the idea is do some angle chasing next. Like basically, in order to prove that angle, like to prove that VIC collinear, we want to show the angle VCB minus the angle ICB is equal to 0 degree. Like we want to show that the two angles like are actually the same angle, which means that like we can do a subtraction and we get the we like so we do a subtraction and we get the same angle. So here, well, we gotta do a subtraction here, and try to see that it's the same angle. Well, why is that the case? Well, let's look at the angle VCB. What's the angle VCB equal to? Oh, yes. I see it. Okay. So basically, if you look at this diagram here, is that you notice that you have an isosceles triangle as a result. Like this is the isosceles triangle, because of the fact that point M is the center of the circle. So therefore, we have that. So therefore, we can say that the angle V is that the angle VMB is equal to 2 times the angle VCB, right? Because the exterior angle is the sum of the two remote interior angles. But because we have an isosceles triangle, so therefore the angle VCB is twice as the angle VMB is twice as the angle VCB, right? But also notice that because we know that MP is mid segment of triangle BAC. So therefore we have the MP is parallel to CA. So therefore we can use the parallel line axiom that we have the angle PMB is which is like VMB, because V is on the line, construction V is on line. So PMB is equal to the angle ACB. So therefore we have the angle ACB is equal to 2 times the angle VCB, which means that the angle VCB is equal to half of that. So the angle VCB is equal to half of angle ACB, which is which is to have angle C over 2, which is equal to angle ICB. Okay, because I is the in center. Okay, so therefore the subtraction is 0. Okay, so we're done. Okay, so this tells us that the proof is done. It is VIC collinear. Okay, so that's the first part of this problem. Okay, well here, like to solve this problem, like we have to take a look at this diagram. Like there are a lot of cyclic quadrilaterals. Like, if there are very few cyclic quadrilaterals, like those problems tend to be easier. This problem is a little bit more difficult because there are more cyclic quadrilaterals, but it's also not that bad. Like you have several choices. Like that's probably why this is number 6 on the USHMO. Okay. But here we have this cyclic quadrilateral, like and that allows you to prove that VIC collinear. Okay. So that's the first part of the problem. Okay. Like you want to prove that I lies on the ray C, which is like VIC collinear. Okay. And then the next thing we want to prove is that the line XI bisects UV. Okay. So let's look at this diagram again. Okay. I'm gonna duplicate the slide. Okay. Okay. So we want to prove that this line XI bisects the segment UV. Okay. Well, okay. So where's X? This problem also tells us like at the like we also have the point X. Okay. And the point X is the midpoint of the like X is the midpoint of the major like of the ray BAC. Okay, that's how like it's the midpoint of this arc. Okay, and we want to show that XI bisects the line the XI bisects the line XU. Okay. Okay. So how do we solve this problem? Okay. And this is a very useful technique. I've seen that being used in several problems on the USAJMO and the USMO in geometry. Okay? And as like whenever we have a circumscribed circle with the in-center setup, okay? Like this is a very important setup. You need to be able to do it. Is whenever uh we have a triangle, okay? Uh, and then we have the in-center, okay? Like what do we do in this type of setup? Okay. Okay, what do we do? Okay. The idea is we extend, like we draw the angle bisector, okay? Because BI is the angle bisector, okay? So the first thing you need to like first thing you know is that like this point here is the midpoint of the arc AC. Okay, because we know that so here let's say this point is well we claim that this is M, okay? Is that like this point is the midpoint of the arc AC. It's because we know that the arc AM is equal to angle ABM, but that is equal to angle MBC, so that is equal to the arc MC, right? So therefore, you have the midpoint of the arc, right? But furthermore, there's something very interesting right here. Right? Is the in-center excenter lemma. Okay? Like it also goes to in-center excenter lemma, right? And that is if you consider X circle, like the center of the X squared circle, like you have the like it's actually like what you do is you draw a circle center M, okay? Draw a circle center M. Wait, hold on. Something is wrong. Maybe point M is not here. Like this is always true. Okay, is that like if you draw a circle center M, okay, maybe I is a different place because I just eyeball the point I. So that might not be point where point I is, eh? Maybe this is the point I, eh? Like basically the in-center x-center lemma um tells us that uh the circumcircle of AIC is actually point M, right? And also this circle, this like this like this circle also goes through the center of the circumscribed circle of uh like x squared, like it's the x circle, it's the bx circle, like it's the bx center, right? Like basically if you extend this, right, this point here is IB, right? It's the center of the bx circle, right? That is the very important fact, right? Like basically the in-center x-center lemma tells us that M I'm gonna write this is MB instead, is MB is MBA, AMB is equal IMB is equal CMB. This can be proved very easily through angle chasing. Right? The idea is to show that the angles are equal. Right? And then you can also show that this is also equal IBMB. Right? So another way to say this is we have the A, I, C, and then IB is the cyclic quadrilateral with center at the midpoint of the arc AC. Right? So these are the two very important setups you need to know for like for the like very important setups you need to know, right? And we're going to need to use this for some of the problems down the road, right? Yeah, so that's why whenever you have the circumscribed, like you have the circle and you have the in-center, what do we do to the diagram? Is we want to extend the the angle bisector to the circumcircle, okay? Because you get to the midpoint, like you'll get to the midpoint of the arc. You can do a lot of angle chasing as well. Right? Like when you have midpoint of the arc, you can do a lot of interesting angle chasing, right? So here we're gonna use that trick here, right? Like with this diagram, right? Well, this like it's very convenient, right? Because like here, what we just show is that V is on the angle bisector, right? So you might be interested in that angle bisector, right? In this problem, right? Well, so the proof of like part A is proof that V is on the angle bisector, right? Well, what is the equivalent statement to that? Eh? Like what is that equivalent statement to that? Like it's something you don't need to prove again. Like variable symmetry. That's very important. Like once you show something is true, the other like another fact must also be true. Hey, what's that? It's actually u is that by variable symmetry. Um, it's that well what we just did is we proved that it's like so basically what we just proved is that V is on the ray Ci. Okay. So that's the like that was part A. Okay. Well, we can immediately say that by symmetry, we must have what? What must be true? And once we show that V is on the ray Ci, what else must be true? Okay. What point is logically similar to point V? Okay. Well, a lot of times it's like M and N, U and V. Like those points, like that's how we label those points. Okay. So here U and V are logically similar. Okay. So what does that mean? That means that U is on the ray BI. Okay. Like CI is the angle bisector. Okay. So here, this is very important. U is on the ray BI. Okay. You don't need to prove this. Okay. But you could prove it, eh? Like you could do the same thing and prove it, eh? But you don't need to, eh? Like in Olympia level, this should be like obvious, eh? Like this type of thing should be obvious, eh? But of course you can prove it, like you just duplicate the proof, eh? What you just did, eh? Of course I'm not gonna do it because it's a waste of time, eh? To do it here, eh? So we have the U is on the right, eh? Like that's why we extend, eh? Actually I'm gonna label these as red, eh? And oh yeah, by the way, do you have like color pens? Like do you like at home? Do you have color pens? Okay?
Nah.
Because I actually recommend like using color pens for the Amy as well. Hey, like you see what I'm doing? It's like the original diagram in black, but the extra lines, like extra circles in red. And so I can see that oh these lines are interesting, eh? Like these facts are like not in the original diagram. Like so we have this like we have this like these points, right? Yeah. So basically we have the like we have the V is on the angle bisector of angle C, and U is on the angle bisector of angle B. Okay, and then as we said earlier, like we're gonna follow through with our read in the problem, and that's we extend the angle bisectors to the midpoints. Okay, so therefore we're gonna label the midpoints as like this point here as well we already have the point M, right? So let's label them as J and K, okay? Because we haven't used J and K as a variable yet, okay? So here we gonna label these two corresponding points, like these points are corresponding, right? It's J and K. And then you know something very interesting after identifying the line J and K, okay? Like we want to we want to show that IX bisects the like we want to show that IX bisects the line UV. Okay, so the line IX, eh? But IX is a very interesting line, eh? It's let me like do you see something very interesting after drawing these lines? Like do you like train your eyes looking for those type of things? Like do you see something very interesting? Okay, and there's a hidden parallelogram in this diagram. Okay, uh, it's actually this parallelogram. Okay, hey, so you see this parallelogram here? Hey, well, uh, this is why like drawing on the board is nice. Hey, it's like I can translate these. Hey, you see? Well, it looks like almost like overlap. Like, maybe if I draw the fine points, like it will be. Hey, but they are like they should be parallel. Eh? It's like this line here is parallel to this. Eh? This is a parallelogram. Eh? And also another thing you should notice is JK. What's the line JK? Is that this line JK is actually parallel to this line UV. Okay? So that's something that is very interesting. Right? We can prove both things. Okay? Is that the first thing is we want to show that JIKX is a parallelogram. Right? How do we prove parallelogram? Right? Well, angles. Right? Here, length is a little bit more difficult. Like when you have midpoint of arc, it's probably a good idea to deal with angles. Okay, so here let's deal with angles. Okay, so the first thing is the easiest angle to pick off is the angle. Just look at the angle J. No, yeah, angle J. Right, so it's angle XJC. Okay, like that angle is like I would believe like in my opinion it's probably the easiest to pick off. Okay, what's the angle like what's that angle equal to? Well, angle XJC is equal to 1/2 of the arc XKC. Okay, uh but you know that X is the midpoint of the arc of the major arc. Okay, so therefore you can write that the xkc is equal to 360 minus the arc BC. Okay, so therefore this is equal to 180 degrees minus 1/2 of the arc BC. But what's 1/2 of the arc BC? Related to the triangle. That's simply the angle A. Okay, so therefore this is simply equal to like you have this wait, hold on a second. No, no, no. No, no, no. It's 1/2 of the arc XKC. 1/2 of the arc. No, no. Yeah, 1/2 of the arc XKC. That's not. It's actually, let's divide by 2. Furthermore, you have to divide that by 2 because 360 minus like you have to divide this by 2. Okay, actually made a algebraic error here. Okay, like this should be 360 minus BC, the arc BC, and divide by 2 because XKC is only half of the major arc. Okay, like we like in the problem, like the construction is that X is the midpoint of the major arc. So therefore, XKC is only half of it. So it's 360 minus BC over 2. Okay? So we get this is equal to 9 degrees minus the arc BC over 4. Okay? But we know that arc BC over 2 is angle A. Okay? It's like you notice that like the BC, like the arc BC, 1/2 of the arc BC is simply angle BAC. Okay? Like, because like the arc BC, like the arc, you have the corresponding angle is like angle A. So it's angle AO, half BC is AO2. So therefore, this tells us that this is actually 9 degrees minus angle A divided by 2. Okay? So that's what we have here. Okay? And then, well, and then you can also show that what is the angle, like what's the angle KIC, okay? Is that the angle KIC, that is simply the exterior angle of this triangle here, okay? The angle KIC is the exterior angle of this triangle, okay? And the exterior angle is the sum of the two remote interior angles. Okay? So what's that equal to? Okay, well then that is equal to angle B over 2 plus angle C over 2. Okay? But these two things are equivalent. Okay? Like these two things are actually equivalent. Okay? Because we know that the sum of the three angles of a triangle is equal to 180 degrees. Okay? So therefore, A plus B plus C over 2 is equal to 9 degrees. Okay? So therefore, these two things are actually equal. Okay? So therefore, we have these two angles are actually equal. So what does that mean? That means that by parallel axiom of transversals, we have two lines are automatically parallel. Okay? Like essentially, this tells us that. So basically, we can write that. Therefore, we have the angle angle XJC is equal to angle KIC. So therefore, we have the line XJ is parallel to KI. Okay? And then the next thing is we want to prove that the other two lines are parallel. Okay? Well, the idea is show that like if we want to find the angle, like so the first thing that prove that XJ parallel to KI, we use the same side corresponding angles in a transversal are equal. Okay? To prove that XK XK parallel to JI, we need to use same side interior angles add up to 180 degrees. Okay, like that's the other one we're gonna do. Okay, so I'm gonna duplicate the slide here. Okay, and the idea here is like we still need to use the angle XJC. Okay, so we have to actually I'm gonna just go right here. Okay, is that the angle XJC is equal to 9 degrees minus angle A over 2. Okay, and let's try to work out what is the angle JXK. Okay, what's the angle JXK equal to? Okay, well, like that's why like follow the midpoint, okay? Well, we have the angle, like we have the angle x, no, we have the angle jxk. That is equal to 1/2 of the arc JBCK, okay? JBCK, okay? What's that? Okay? Like JBCK, okay? Well, that's simply equal to the arc, like 1/2 of the arc JB plus BC, okay? JBCK. So JB is easy because it has like C over 2. CB is also easy, right? And then what about CK? Okay, well, and then you have CK, right? Okay, what's this equal to? Okay, well, what's 1/2 of JB? Okay, so you have 1/2 of JB, 1/2 of BC, 1/2 of CK. Okay, what's 1/2 of JB? Okay, well, that's simply C over 2. Okay, because that arc is subtended by the angle C over 2. Okay, so this is C over 2, angle C over 2. Okay, how about 1/2 of the arc BC? Okay, that's angle A. Okay, and then the 1/2 of the arc CK. Okay, that's equal to B over 2. Okay, so what do we get? Okay, well, we know that A plus B plus C is 180 degrees. Sum is 180 degrees. So therefore, this becomes like this thing here simply becomes okay. So therefore, this is equal to angle A plus angle B plus angle C over 2 plus angle A over 2. Right? So this is equal to 90 degrees plus angle A over 2. So what does that mean? That means that the sum of these two is equal to 180. Okay? So this tells us that we have the angle XJC plus angle JXK is equal to 180 degrees. Okay? So therefore, by parallel axiom, well, we have the same side interior angles add up to 180. Therefore, the two lines are parallel. Okay? So we have so far we established that these two lines are parallel. Okay? And also these two lines are parallel. Okay? The blue ones are same side correspond angles equal. The green ones are same side interior angles added to 180 degree. Okay? Like both of them uses the angle XJI, okay, to prove it. Okay? So basically this is all angle chasing, okay, showing that we have a parallelogram. Okay? And then well, the next thing is we also want to show that JK is parallel to UV. Okay? Why? Because once we prove that, then well, we know that the diagonals of parallelograms bisect each other. Okay? So therefore, you have this midpoint here. Like the idea is focused on midpoint. Like we have a homosity going on. Okay? Because like we have parallelogram, like we have parallel line. So essentially, it's a homosity. Okay? Is that the point V would correspond to J, Y is correspond to midpoint, and U is correspond to point K. Okay? So if we can show that you have homosity going on, then obviously point Y is the midpoint of UV. Okay? So we want to prove a parallel line. The next is that like the line UV is parallel to the diagonal JK. So we can use the fact that because the diagonals of a parallelogram bisect each other, so we have and we also have homosity, and therefore Y is the midpoint. Okay. Okay. So we're gonna prove that next. Okay. So we're gonna try to prove the two lines are indeed parallel. Okay. How do we prove those two lines are parallel? Okay. Well, okay, so this is what point are they? Okay. This is J and K. Okay. So we label them back as J and K. Okay. Well, the idea is try to find the angle. Is do more angle chasing. Okay. It's like we notice that like so the first thing is we start with the angle UVI. Okay. what's the angle UVI equal to? Well, we want to show that, like, so here we have the UV parallel, like on the side. You can probably write this. It's UV parallel to JK if and only if the angle UVI is equal to angle KJI. Same side corresponding angles are equal. So we should probably start with the angle UVI. So like this is like what we want to show. So we start with one of the angle UVI. What's that equal to? Well, now this is where we use like we use the uh uh cyclic quadrilaterals. Is that if you look at UVI, that's equal to half of the arc UC. So therefore that is half of the arc UC. So therefore this is equal to the angle UBC. It's equal to UBC. But UBC is simply equal to the angle KBC. Well, what's KBC equal to? Well, that's equal half of the arc KC. Half of the arc KC is simply equal to what? That's simply equal to the angle KJC. Right? So we're done. Because KJC is simply KJI. So therefore, we just established that these two angles are equal. So what does that mean? That means that we have parallel. Like that means that this UV is actually parallel to the line JK. We have parallel. So therefore our proof is done. Is that now we just use the fact that is that because so here we just like be like, okay, so we let the IX intersect JK, and we can use N as well. So let's use R. We intersect them at point R. So JK at point R. So this point is point R. Then it's obvious that we have R is midpoint of JK. And because we have parallel lines, it's because we have JK is parallel to UV, then we know that R, like we have a homosity. Is that the line U is that V Y U, this line here has a homosity center I with the scaling factor of JI divided by VI, we'll get to the line JRK. So we have the homosity. So therefore, or you can just think about it, it's a scaling thing. So it's obvious that. So therefore, this tells us that Y and R are corresponding, right? And because we know that, so therefore this tells us that Y is the midpoint. Because we know R is the midpoint, so Y must also be midpoint of UV, and we're done. Okay. So that is how we prove this problem. Well, I can tell you that like when I look at this problem, it's actually a little bit shorter. Like the time for this problem, I think it's like about 30 to 40 minutes at most. Like question 2 took me a while. Like this is very important. Like as you see, like I just talked about these problems. Like obviously I know how to solve these problems. So like after that, that's quick. But initially, like these type of problems will take me like 30 minutes or so, like to solve each problem. And that's reasonable because like on the USMO you have 4 hours for 3 problems. Like this problem, like I think it was like 30 minutes, while the one before, it was like question 2. This one, the diagram is a lot simpler. This one actually took me a lot longer to figure out. Like cause like to show that it's the equilateral triangle, I was like, what is going on? Like how did I even do it? Like that one took a while. But this one is like this one like I kind of know what to do the angle chase because I know the important setup. It's like you want to extend the line, like you want to extend the line, to the midpoint. Right? So like it's just a very reasonable thing to do. Right? So that's how I end up prove this problem. Right? Uh, yeah. Let's take a look at the next example. The next example is this problem from the 2016 USJMO question 2. This question is actually, the idea is very similar to the previous problem. So let's look at this problem. So here, what do we have? Is that we're given that ABC is the isosceles triangle. In isosceles triangle, AB is equal to AC. Is inscribed in the circle omega. So here we're given that AB equal to AC. Okay? That's why we draw a triangle that looks like it's isosceles, because this is the isosceles triangle. And then we have a circumscribed circle. And then what do we do next? Is when we let P be a variable point on the arc BC that does not contain A. Okay, I see. So here P is a variable point. So we can move this point P around. On the arc BC that contain A. Okay, so it's the opposite from A. Okay. And then what we do next is, like, here there are two triangles. Here we define this IB and IC. What's IB? IB is the in-center. It's the in-centers of triangles ABP and ACP respectively. So here is not the X. Like we usually label like IBIC as the center of the X circle. Here is not the case. Like those are actually the in-centers of the two triangles. So we have the IB and IC. Okay, and then we want to show that the circle, like if we draw the circle that goes to P IBI. So basically, like the point P will define IB and IC. P is an arbitrary point. But we want to show that the circumcircle of P, like the circumcircle of IB, IC, and point P go through a constant point, passes through a fixed point. Well, what you can do is you can draw first of all, like you draw the triangle APC, like an isosceles triangle APC, and then you draw point P. So you fix the diagram. Like first thing you fix the diagram, fix the triangle APC. And then on the exam, like what you can do is like you just duplicate a lot of the same diagram. And then you pick the point P. Like you pick the point P, like for example here. Let's say you pick a point P here. You draw the two setups, and then you try to see what's going on. And it's actually not that hard to see that if you draw several diagrams, that the desired point is actually the intersection of the two circles. Like it's actually this point. It's not just the intersection, but also what's that? That seems like that's also the midpoint of the arc BC. That is what we're gonna prove. It's like we're gonna prove an even stronger statement than this. It's like we want to prove that the circles pass through a fixed point. Well, instead of doing that, we want to show that point, the midpoint is actually that point, which means that we want to prove that M, P, I, B, I, C cyclic. So that's what we're gonna do. Is here we're gonna be like, okay, let M be the let M be the midpoint of the arc BC. So basically we want to show that M, P, I, C, I, B cyclic. Okay, so how do we do that? Well, remember what we said earlier. Here we have a circumcircle, and we have the incenter. What do we do? Okay, same thing. Okay, draw the angle bisector, draw it all the way to the circumcircle. Okay, so therefore the two lines we're gonna draw two lines. Okay, so this setup. Okay, we draw this line here. We draw this line. Okay, very natural thing to do. Okay, uh, yeah. So we draw this. Okay. And then we're going to label these points as D and E, for example. Right? There's no D and E in the diagram, so let's label them as point D and point E. Okay. Okay. So now, like looking at the diagram, there is something very interesting going on. Is like here, let's mark some lengths that are obviously equal. Okay, like we gotta mark some lengths that are obviously equal. And what lengths are obviously equal? Okay, well we know that AB equal AC. Okay, so here like we have the midpoint. So let's mark the lengths that are obviously equal in the same color. Okay, so we have this line. I'm gonna draw it in green. Okay, it's like this line. Okay, this line here. Okay, this is the in-center, x-center lemma. Okay, these three lines are obviously equal. Okay, by in-center, x-center lemma. Okay, but also you know that because like of the midpoint, right, is that these are also in green as well. Right, because like it corresponds to the same arc. Right, so you have these are also in green. Okay, so this is in green. We also have this line here in green, this line here. Okay, so you have these lines are all in green. Right? You have in center, x center lemma, but we also have these lines in green. Right? Well, now after marking these with colors, there's something very interesting. It's like do you see a congruent triangle? Like there is actually some congruent triangle going on in this diagram. Okay, and yeah, like it's essentially like you need to be like do you see uh do you see the like the congruent triangle? Like after like that's why we mark them with colors. Okay, so we could like look at the diagram and like do the length chasing, angle chasing. That's very useful. Okay, here we mark the lengths are obviously equal. Like you have the in-center, x-center lemma, so you have two sets of lines. Like two sets of lines have the equal length, right? But there's more to it. Okay, it's like there are more subs that are equal, right? And that is what is actually these two lines, right? So I'm gonna mark two more lines that are equal. Okay, it's these two lines are equal. Okay, why? Because point M is the midpoint of the arc BC. Okay, like you have the MD. Right? That arc is the same. Right? Like the arc MD is equal to one half of the arc P no one half of the arc AC, right? Because D is the midpoint of uh uh, because all the arc lengths are equal, so you have the DM has to be equal to ME, okay? And then from here, right? This is where we have like we have two triangles are congruent, okay, as a result, okay, as these two triangles are congruent, okay, okay. Is we want to show that, okay, so therefore like you see like here we have the green length, purple length, okay, so this tells us that okay, it's like after marking the lines that equal, we have the DM is equal to dm is equal to em, right? And also I should say dib is equal to eic. Okay, this point is e. Okay, and then we also have the angle mdp. Okay, like the angle d of these two triangles. I should say mdp. mdp is equal to 1/2 of the arc mp, and that is equal to the angle MEP. Okay, so you have these angles are equal. So what does that mean? That means you have two triangles are congruent. Okay, like these two triangles are essentially congruent. Okay, this triangle here and this triangle here by SAS congruence. Okay, so that is very useful. Knowing that like these two angles are congruent. So what does that mean? That means that we have. So therefore, here this tells us that we have the triangle DMIB is congruent to triangle EMIC by SAS congruence. Two sides and their included angle. Well, when we have two sides and included angle are congruent, like when we have two triangles are congruent, then the corresponding parts of congruent triangles must be congruent. And here we are interested in proving the we want to show that essentially we want to show that the angle IBMIC, that is equal to the angle IBPC, like 4-point cyclic. So we are interested in those angles. Well, here because the two triangles are congruent, then we have the corresponding parts of congruent triangles must be congruent. So therefore, we can say that the angle IBMD must be equal to the angle ICME. Right? And because of that, right? Actually, let's work with the angle IBMIC. Right? So therefore, this tells us that angle IBMIC. What is that equal to? Well, that can be split into the angle IBME plus the angle ICME. But this angle ICME will be exchanged as the angle IBMD. That the sum of these two angles is simply equal to angle DME. So we get this is equal to angle DME. But what's the angle DME equal to? Well, what's the angle DME equal to? That's equal to half of the arc DE. So this is equal to like this angle DME is equal to half of the arc DE, but half of the arc DE is simply equal to the angle IBPC. No, IBPIC. So therefore, we just established that these two angles are congruent, and that is why the problem is done. Like we have this butterfly angle equal idea. So therefore, it tells us that we have, so therefore, this means that we have the IBMPIC cyclic, which means that the circumcircle of IBPIC always goes through the fixed point M. Because the point M is a fixed point. And we're done. Right? So what do we do in this problem? Right? Well, two problems. The solution is the solutions of these two problems very similar. Okay, what do we do? Is whenever we have like the inscribed circle, whenever we have the in center, and we have a circumscribed circle, it's a very good idea to extend the like you draw a line through the like you draw the angle bisector and extend it all the way to the midpoint, okay, of the circle. And then you do a lot of angle chasing and length chasing like that. Okay? And also like sometimes like you do the in center extender lemma. Okay? So a lot of interesting things you can deal with in these type of problems. Okay? And that's how we solve these two problems. Okay. Okay. So I want to talk about this problem instead. Like this problem like is like you definitely have not looked at this problem. Like I want to focus on like spend like 45 minutes on 3D geometry. Okay. So let's take a look at this problem. Okay. Like these two, like this problem and the previous one is very similar. Okay. But I want to look at this first. Okay. So what we have here is like this problem is from the last year's Amy 2 question number 14. It looks very scary. Like this diagram is not provided on the actual Amy. Okay. So you're responsible to figure out what's going on. Okay. But we draw the diagram like I just took the diagram from AOPS. Hey, but I'm gonna solve this. Hey, I'm gonna solve the problem. Hey, hey, like I actually have a very interesting way to solve this. Hey? So here, what we have is like oh, wait, hold on. Okay, is we have the cube. Okay, is we have a cube shaped container has the vertices of A, B, C, D, where A, B, and C, D are parallel edges of a cube, and AC and BD are diagonals of the faces, diagonal faces of the cube. Right? So we have this diagram like this. Right? Like the A, B, and C, D are not on the same square. Right? In fact, if you think about the edges like A, B, C, D, like that is actually like a rectangle. Okay. And then what we know is that the vertex. So basically, there's a plane. Okay, like there's a plane. Okay, and then we place the point A of the cube on the plane. Okay, so we have the point A on the plane, and we also know that vertex B is 2 meters above the point P. Okay. So basically, we have the point we have the point B is point B is is 2 meters above point P. Okay, and then we also have the point C is okay. So we have point C is 8 meters. Okay, so yeah, this is 8 meters. Okay, and then point B is 2 meters above. Okay, point D is 10 meters above. Okay, and we also have the this is a very interesting fact. Okay, is that like the diagram is oriented in a way that ABCD is perpendicular to the plane P. Okay. Well, whenever we have a 3D geometry problem, what should we do? Okay, this is a very important technique. Right, not just for the Amy. Like I actually seen several AMC problems. But they are usually one of the later problem on AMC, like number 23, 24, and AMC 12. Okay, 3D geometry. What do we do whenever we have a 3D geometry problem? Okay, what's some technique? Okay, Lawson, like what are some problem technique that like whenever we have a 3D geo
By
problem?
taking a cross section like A, B,
Exactly,
C, D.
exactly, the cross section, and here a very reasonable cross section is the plane ABCD, right? Because we're told that the rectangle ABCD is perpendicular to plane P. Okay, so essentially what we have here is like we have a plane P, and then we have this like perpendicular plane. Okay, but the ABCD is uh not in this orientation, but it's actually a tilted orientation, because we know that this is a perpendicular to plane P. Like we know that A is on the plane. Okay, so basically A is like this. Okay, B is actually slightly tilted up. Okay, so it looks something like this instead. Okay, like this is what ABCD looks like. Okay? Like you have to like we draw this cross section. This not ABCD. It's actually ABDC. Uh, Wait, hold on. So the diagram is labeled a little bit. Hold on. I mean A B C D. The rectangle A B C D. Well, um,
Sure, the original labeling is correct. It's just a rectangle ABDC.
oh, the original is ABDC.
Yeah,
Yeah, the thing is like if we label it like that, like
because
we
AC
can
and
have
BD are face diagonals.
AB, yeah, AC and yeah. So the original so it should be okay. So this is actually wrong. It's actually should be ABDC. Yeah. You have AC and BD on face diagonal. Yeah, exactly. So the drawing is correct. It's just that it should be ABDC. Yeah. I just grabbed this like the prompt, like just copy and paste. So whatever they like, probably there's a typo in the prompt. So here it should be ABDC. Like it's like this. Because we know that like this is a cross section. Like the point B should not be on the plane P, because like if you have the line, this line is on the plane P, so we draw that cross section. What do we notice here? There's something very interesting. Is that now let's just draw that purple plane. Like draw that purple plane. There's something very interesting right here. Like this is a very important technique. Like you draw sub-diagrams. Like whenever you have 3D geometry problem, just break down the problem like with sub-diagrams like this. So you have the point A here, B, D, C. Well, we know that C is 8 units above the plane A. Like because this is like this line here is like where the plane P is. Well, we know that A is right on the plane P. That's why we have the A is on the ground. And then we know that C is 8 meters above. B is 2 meters above. B is 2 meters above. And then D is 10 meters above. Well, what do we notice here? It's because we have right angle that we have similar triangles. You see that these two triangles are clearly similar. Because you have right angle stuff, you have like you just do those like 90 minus x stuff, right? Like these two triangles are similar, right? And because we know that AC is diagonal of the square, then we can write this as s squared 2 and AB as s. That you can easily see that the ratio of these two triangles, like the side line ratio, has to be square root 2 to 1. Like these two triangles are similar. So here you can easily see that the two triangles with ratio of root 2 to 1. Like the larger triangle to small triangle, root 2 to 1, because the hypotenuse clearly has the ratio of root 2 to 1. So what does that mean? That means that we can write the length, like we can write the horizontal length. It's 2 root 2. That's obvious now. And then 4 root 2. So what does that mean? We can calculate the s. So therefore S square root of 4 root 2 square plus 2 square. And that's equal to square root of 32 plus 4. So that's equal to 6. Okay. So this tells us that the cube has the side length of 6, which means that if we want to find the volume of the cube, well, we want to like when we want to find the volume of the water, we want to find the volume well, we obviously have the volume of the cube. That's 216 now. Okay. So therefore, knowing the volume of the cube, we can just find the volume of the air above. Right? Like we don't want to find the volume of the water. Like that's just too difficult. Right? Because like the water there is a lot more complex to find than the volume of the air above. Okay? So therefore, we just need to find the volume of the air above, and then subtract it from the volume of the cube, and that will give us the volume of the water. Okay. So here, let's try to find the volume of the air above. Okay. Okay. So what is the how can we get the volume of the air above? Well, we need to find out something interesting. Uh, like like we can find out something very interesting with the water like the air on top. Okay. So what do we do in this problem here? Is maybe let's try to find out something about this this shape on top. What is this? And find out what's this shape on top. What is that? Well, we need to find the dimensions of that. Like the relative dimensions of that. And what is this? It's actually you can pretty much see that um like how do you find the volume of that? The idea is you extend it to get to get the uh to get a bigger pyramid. Like you take a bigger pyramid, subtract the small pyramid. Right? Like that's what we do. Like if you take a bigger pyramid, subtract the small pyramid. Right? That's how you get the volume of the that air. Okay? Like it's like there's no formula for the volume of those really weird shape, but you can also consider using the volume of the extended to get similar pyramids, which allows you to calculate the volume of each of those. Well, how do we calculate something about those pyramids? Well, okay, so let's do the next thing. Like how do we end up calculating that? Well, the idea is we want to calculate what are these two triangles. Like we want to think about what are these two triangles. So the first thing is notice that this plane, like this plane is a vertical plane. Remember that this plane is a vertical plane. A B C D. This is vertical. Uh so what does that mean? That means that the water level has to be horizontal. Okay, it means the water level, uh, the water level, has to be horizontal because, well, obviously the water level has to be horizontal. Okay, and that's very important. Okay, is that now if you look at this triangle, if you look at this, look at this square, look at the square on the side. If you look at this square here on the side. Is that you have a horizontal water level. Like this line here, even though it's slightly tilted forward, it's not tilted on the side. Yes, it's tilted a little bit forward you. Like tilted forward. It's not that it's horizontal. It's not. It's like the nice thing is in 3D, it's tilted forward toward you. It's not tilted on the sideways because that plane is vertical plane. What's important about that is that this tells us that the water level is horizontal. That means that the water level has to be parallel to the diagonal. That is the important observation. Is that these two lines are parallel, which means that the empty air on top, like it creates two, like it creates the two isosceles right triangles. Right? That's what I was saying. Right? Is that here? It means that these two triangles, right, are isosceles right triangles. Okay? So therefore, we want to find what are those two isosceles right triangles. Like, what are they? Okay? So here, what we do is we're gonna label these points. Okay? So we have this is C and D. Okay? Actually, yeah, C and D. And then let's label this as E and F. Okay? And then this is E, F, G. Okay? So let's look at the like something about the triangle CEF, right? Well, again here we're gonna draw some cross sections, right? Well, the idea here is is you go back to that vertical cross section, right? Like now let's go back to this vertical cross section, okay? Is you have this is right? So basically you have this is like 6 root 2, and this is 6, and this is 2 units above. Okay, so the distance above is like this is 8, this is 2, and this is 10. Okay. Well, we know that the horizontal, like this is why you like it's important to know that the water level is 7 units above. Right. So what do? Is you draw the water level that's 7 units above. Right? So this is the water level. Right. So here, this is the water level. Okay. This is the water level. Okay, horizontal. Okay, water level. Okay. Where's point G? Okay, where's point G? Okay, point G is actually right here. Okay, it's the intersection point on the right. Okay, and this is C, and this is the A. Okay, that is the interesting thing. Is that point G is on the line AC. Okay, so what does that mean? That means that we can actually find the length of CG by similar triangles. Okay? Is that you notice that there's two similar triangles, like the very smallest triangle and a large right triangle. Okay? Those two triangles, what are the ratios? Okay? It's 1 to 7, no, 1 to 8. Okay? Because the bottom length is 8, so therefore the top length is 1. The bottom length is 7, so the top length is 1. Okay? So the ratio of these two triangles is 1 to 8 ratio. Okay? So therefore, we know that CG is actually equal to 1/8 the length of CA. Okay, so therefore that is equal to what's that equal? That's equal to 6 root 2 over 8, which means that this is equal to 3 square root 2 over 4. Okay, so we get the length of CG, right, which allows us to calculate the like the relative length of the triangle CEF. Right, is that for triangle CEF, like you know that you have a right triangle CEF, and then you have the CG is the altitude, like the CG has the length of 3 square root 2 over 4. Okay, so therefore the length of CE is you have to multiply by square root 2. Okay, so therefore CE has the length of 3 over 2. Right? And EF would have the length of 3 root 2 over 2. Okay? So we just found a lot of things about the triangle CEF, right? Well, let's do the same thing regarding the triangle, like the isosceles right triangle on the right side, right? Like with the vertex of D, right? Well, do we need to do the same thing? Not really, right? Because we can do like, I mean, well, we gotta do something very similar, but the most important thing is focus on that midpoint, right? We label that midpoint as H, right? Is that where's the H, right? Is that you have D here, like this is why you label a point correctly, right? Is that the point H is this point here, right? This is the point H. So we want to find the length of the H. How do we do that, right? Well, the idea is we want to construct similar triangle, and the similar triangles is actually these two similar triangles, right? Is you consider these two similar triangles instead. Okay. So what do we have here? Is that you have these two similar triangles. You have the D and then H. Okay. And then this is a B. Okay, well, label the lengths. Okay, the lengths are not 10 anymore. Okay, is that the entire height is actually 8. Is 10 minus 2 is 8. Okay, and then this length here, what is that? That's 5. It is 7 minus 2 is 5. So therefore the top is actually 3. Okay, so that means that DH, like this tells us that DH is equal to 3/8 the length of DB. Okay, so we have the length of DH is 3/8 of the length of DB, which is equal to, like, that's essentially equal to 3 times the length of CG, right? Because like we know that CG is 1/8 of CA, right? So therefore you don't need to do everything again, right? Then you know that this triangle, like the triangle on the right side, is similar and also 3 times the length of triangle CEF. Right? That's crucial in this problem. Right? Knowing that it's 3 times the length, right? So what does that mean? That means that if you extend this, right? Like what you want to do is you want to find the, like, so basically it tells you that the small like you have the small like, so you have the essentially the small pyramid. It has 1/27 the volume of the large pyramid, right? Because the ratio of the length is 1:3 ratio, okay? So therefore, what you want to do here is you want to calculate that. So the next step is you want to calculate the volume of large pyramid. Then like, that's easy, right? Why? Because you can do the length chasing, right? Like, oh yeah, so this is 6, right? Like, you know, this is 6 here, right? Side length of the cube is 6. So therefore, you have 1:3 ratio, so this is 3. Okay, so this is 3. And you also have this length here, like these two lengths are 3 times of what you have, so it's 9/2. Okay, 9/2 each. Okay, so basically, this is the right pyramid. Okay, like you have a right pyramid, like you have a right pyramid here. Okay, right pyramid. The lengths are 9/2, 9/2, and then this is 9. Okay, yeah, 9. 9/2, 9. And then the small one is 1/3 of it. Okay, it's on top. Okay, so therefore the volume of the air is equal to 1 minus 1 cube 1/3 cube times the volume of the large pyramid, which is equal to 26/27 times the volume of the pyramid. Because you know the side length is 1:3 ratio, so the small one is 1/27 of the volume of the large pyramid. Okay? So you just do the multiplication. It's 1/6 times 1/6 ABC. Okay? That's 1/6 times 9/2 times 9/2 times 9. Okay? And then we cancel as much as we can. Okay? 3, 9, this is 2. Okay? Well, now you can solve this is 13. Okay, so you get this is equal to 4, and numerator is 117. Okay, so that's the volume of the air. Okay, which means that the volume of the water is equal to 216 minus that. Okay, whatever that is. Okay, that is equal to 864 minus 117. Okay, hopefully this is correct. I'm not sure. Okay, it's 747/4. Okay, so the answer is 747/4, and that's the volume of the water. Okay, so what does that mean? That means that well, you know, it's a 747/4, which means that the answer is 751. Okay, so what's the idea of this problem? Okay, well, we're gonna do like more problems, like actually like I have to go now a bit. Like we're gonna like the next class is gonna be like 15 minutes longer. Like we're gonna go for an extra problem, right? Next class, eh? And what's the main idea of this problem is we want to draw important cross sections. Right? Like in 3D, you can see that like that's a very important strategy. Right? Like draw multiple cross sections, like not just one cross section, and that is how you end up solving this problem. Okay. But yeah. Anyways, yeah. Talk to you next week. Like like we're gonna have class next week. Like yeah. Talk to you next
Okay.
week. Bye.
Thank you.